Section 8.7, finding rational roots. The objectives here are to determine the rational roots of any polynomial function with integral coefficients, those are integers, and to attempt to identify any remaining irrational roots or imaginary roots. Now, the rational root theorem states the following. If a function with integral coefficients is given by the following, where a of n is the leading coefficient and a sub 0 is the constant term at the end, then any rational root of this function, remember rational root means the number has to be rational itself, like a fraction or a terminating or repeating decimal, any rational root of this function will be given by plus or minus p over q, where p is a factor of the constant term and q is a factor of the leading coefficient. So let's first see this with an example that we know the roots of. So verify that the roots of the following equations satisfy the rational root theorem. So if we knew that this factored into this, we could say, well, let's split this up. This becomes, right, we'll set each of these factors equal to 0. Okay? So solving each of those when set equal to 0, those are the three roots that we get as results. 4, 2/3, and negative 5/4. Well, let's take a look at the rational root theorem now. The rational root theorem again says that all the possible roots that could exist that are rational are considered to be factors of this over factors of this. Well, what are the factors of 40? The factors of 40, there's a lot of them. 1, 2, 4, 5, 8, 10, 20, and 40. And what are the factors of 12? We're going to have 1, 2, 3, 4, 6, and 12. So these are really the factors, again, of 40, which is considered to be p, right? P is any factor of this. So these are the possible values that p could take on. These are the possible values that q could take on. So again, the factors of this number are always p. The factors of this number are always q. Now we can look at all the possible ratios of p to q, remembering that all of these numbers can be plus or minus, because how would you get 40, right? You can get 40 from 1 times 40 or negative 1 times negative 40. So every one of these signs is really plus or minus. I'm not going to write it tons of times. I'll write it in the front so I know. But all these numbers can be positive or negative. Now, what we'll see is that how could we possibly get 4 as a root? Well, it could simply just be this p-value over this q-value. That'll give us 4. Or it could be this p-value over this q-value. That'll give us 4. Anything else? No, that's it. Nothing else when dividing one of the p's by q's gives you 4. But all that matters is that one of them possibly does. Okay, so this is true. This is definitely approved by the rational root theorem. How could you get 2/3? Well, take this 2 divided by this 3. Or take this 4 divided by this 6. Or this 8 divided by this 12. Any of those ratios of p to q would reduce to give you 2/3. And then finally, negative 5/4. Well, I'll write this one in green so we can see it. Here's the 5, here's the 4. And that works perfectly. Or, is there anything else we can do? Let's see. No, that's it. Those are the only ones that reduce. Now remember that the 5 and 4 could be plus or minus, so the negative sign is okay as well. So all three of these roots do come about as some ratio of p to q. If I were to list all the possible roots, you would literally have to list all the p's and q possibilities. So you start with I personally start with the biggest p value first. So 40 could be over 12, 40 could be over 6, 40 could be over 4, 40 over 3, 40 over 2, and 40 over 1. Those are all the possible values from this p and any of these q's. Now, these will reduce, and it is important to reduce them because then you can roll out repetitive possible roots. 40 over 12, if we reduce them both by a factor of 4, become 10/3. 40 over 6, if we reduce them by a factor of 2, would become 20 over 3. 40 over 4 is just simply 10. 40 over 3, well, that can't be reduced at all, so we're going to leave that as 40 over 3. 40 over 2 is 20, and 40 over 1 is just 40. So these are the possible roots from just using one of the p's and all of the q's. That's 1, 2, 3, 4, 5, 6 possible roots already. Now, you then have to do the same process as 20 over all of these. But what you'll notice is that some of them will repeat. For example, 20 over 1, well, that's already here, so we don't have to write that on again. 20 over 2, well, 20 over 2 is 10. That's already here also. 20 over 3, that's listed here also. 20 over 4, though, what's 20 over 4? 20 over 4 is 5. So we have not listed that yet, so let's add 5 to the end. Then we can go with 20 over 6. Well, 20 over 6 is 10/3. That's already there. And then find the last part, 20 over 12. 20 over 12, reduce them both by 4. We're going to get a result of 5 over 3, and that's a new one. We don't have that yet. So 5/3. Remembering that all of these are really plus or minus. Now, what we can do really is go through this process with all of them. So we did 40 and we did 20. Next, we would go to 10 and try pairing up 10 with all of these and continuing and continuing and continuing. Stop here because the objective was just to prove that the roots are possible p's over q's, and we saw that already. 4 shows up already, 2/3 shows up, and negative 5/4 shows up just by picking values from here and here and writing as p over q. So let's take a look and go through a general approach to finding roots. First, using this rational root theorem, and these are rational roots we're looking at, list all the possible rational roots, list all the p's over q's that exist. Then use a graphing calculator to determine which of these possible roots may actually be roots. So if you get a root of like 20 over 7, well, that's around 3. And if you see an x-intercept around x equals 3, then there's a good chance that that one is one of your rational roots. Now, depending on which ones show up on the graphing calculator, use a synthetic division table to show that the number is indeed a root. And eventually you can reduce this equation down to a second-degree polynomial or a depressed equation. And then once you get down to a second-degree polynomial, you can use the quadratic formula or factoring to determine the final two roots. And those final two roots may or may not be rational. They could be imaginary. They could be irrational. But the idea is that we want to get down to a depressed equation that's quadratic in nature. So let's look at example 2. Using the rational root theorem, determine with evidence the location of the zeros of the following function. So let's list all the p's and all the q's. The p values are the factors of 10. So plus or minus 1, 2, 5, and 10. The q values are plus or minus 1, 2, 3, and 6. Again, now we'll take a look at the ratio of p to q and list all our possibilities. So start with 10. It could be 10 over 6, 10 over 3, 10 over 2, and 10 over 1. Again, take 10 and put it over all 4 of these to see what you get. Reduce these, please. Reduce them all in the next line. 10 over 6 is really 5/3. 10/3 is still 10/3. 10 over 2 is just 5. And 10 over 1 is just 10. Now I'll do the same thing with 5. 5 over 6, well, that's new. 5 over 3, well, that's already showing up right here. I don't have to list it again. 5 over 2, that's a new one as well. And then 5 over 1, well, 5 over 1 is already right here listed. So then we go down to 2. Let's take 2 and put it over these. 2 over 6, well, that's 1/3. That's a new one. 2 over 3, that's 2/3. That's a new one. 2 over 2, that's 1. Well, 1 hasn't been listed yet either, so we have to still list 1. I'm going to go down here and continue. And then finally, the last one, we'll do 2 over 1, which is just 2, and that has not been listed either. And then finally, the last possibility is taking 1 and putting it over all of these. So we've got 1 over 6, 1 over 3, 1 over 2, 1 over 1. 1 over 6 is new. 1 over 3 already shows up right here. 1 over 2 is new. And then 1 over 1 is just 1, and that already also shows up right here. So this is our list of possible rational roots. Now remember that all of these could be plus or minus. So they could be positive or negative. So what we want to do next is really take a look at our graphing calculator and get an idea of which of these possibilities is closest to our roots on a graphing calculator. So what we'll do now is take a look at the graph of this and get an idea of which of these possible rational roots may or may not be the actual root. And what we'll do is we'll try to figure it out here. Like clearly this is going through 2, and that's one of our roots right there, positive 2. This is at 2.5, and that's 5 over 2 right there. And it looks like this one is back here somewhere, which is a little bit difficult to see. So I probably wouldn't choose this to test in a synthetic table. I would choose 2 as one of my roots, run it through a synthetic table, and then take a look at the depressed equation that results. So to do that, we make our synthetic table. We go ahead and put our coefficients along the top, 6, negative 25, 21, and 10. We'll test 2, since 2 makes the most sense. Bring down the 6. This is 12. 12 minus 25 is negative 13. Negative 26, negative 25, negative 26 and 21 is negative 5. This gives me negative 10. Negative 10 and 10 is 0. So this indeed is a root. Remember, whenever the remainder is 0, it's a root. Now the cool part is that I get a depressed equation from this. The depressed equation is 6x squared minus 13x minus 5. And that can be factored further. So we could either test 2.5 again in this equation, or we can factor it further. I mean, it's not difficult to factor, but you can use another synthetic table if you'd like to. I would just factor into 3x plus 1, 2x minus 5, okay? And then as a result, if I want to find the roots, remember, set it equal to 0 and solve. And what we'll notice is that the roots from this turn out to be as we had expected. 5 halves, that's the one that we saw originally, and then this root turns out to be negative 1/3. So all three of our roots, we have negative 1/3, 5 halves, and x equals 2. 3 roots because it was x to the third power. And again, there's a possibility that once you get this original rational root, that these two remaining roots may indeed be irrational or imaginary. So if you can't factor this, use the quadratic formula to figure out what the two remaining roots are. Example 3. If the velocity in feet per second of a particle defined on the interval from 0 to 5 seconds is given by the function v of t equals 6t to the fourth minus 41t to the third plus 105t squared minus 113t plus 35, then determine when the particle is at rest. Well, for a particle to be at rest, or something not to be moving, it has to have no velocity. And since this is the velocity function, we'll just go ahead and set it equal to 0. So in reality, what we're doing is we're finding the zeros of the function v of t, or we're finding the roots of the equation when this is set equal to 0. We're finding the roots. So we'll use the rational root theorem. So we'll start by listing all the possible values of p's over q's. Well, let's see, 35 is 1, 5, 7, 35. And then 6 is going to be 1, 2, 3, 6. Now we take all the possible p values over all the possible q values, which, is pretty easy actually. So start with this one. So we've got 35. Again, all these are plus or minus always. 35 over 6, 35 over 3, 35 over 2, and 35 over 1. Then we go to the next number, 7 over 6, 7 over 3, 7 over 2, 7 over 1, 5 over 6, 5 over 3, 5 over 2, 5 over 1, and then finally 1 over 6, 1 over 3, 1 over 2, 1 over 1. Now, in all of these cases, what we'll notice is that they're not in the restricted domain. So if we're looking at the restricted domain from 0 to 5, this list is dramatically reduced. So from 0 to 5, the only possible values are 1 and 5 right away, obviously. Okay, we get that from here, get that from here. Then after that, we've got a bunch of fractions that will work also. 1 half, 5 halves, 7 halves, 1/3, 5/3, 7/3, 1/6, 5/6, 7/6. Now, to me, it makes more sense to go ahead and look at the graph right away, because if 1 or 5 are possibilities, then we should definitely test that. So let's take a look at the graph now. Alright, so here's our graph zoomed into the right domain that we're looking in. We're really only looking from 1 to 5, from 0 to 5 here, but we'll notice that the roots on this graph only lie here and here. Okay, this continues upward. So it looks like it's right around 1/2, like it's right on 1/2, and we see there's 1/2 as a choice. And here it's between 2 and 2.5, but it's not 2 1/4, it's probably 2 1/3, which would be 7/3, and it looks like 7/3 is right there. So I could pretty much choose the 1/2 or the 7/3 right now. I'll choose the 1/2 to try, because it's a little bit easier. Alright. Let's get rid of the graph so we can do this. Alright. So let's draw or write our synthetic table. We'll start, we have 6, negative 41, 105, negative 113, and 35. So we'll start with 1/2. Bring down the 6, multiply and add negative 41, we get negative 38, 1 half times negative 38 plus 105 is 86. 1 half times 86 minus 113 is negative 70. And then half of negative 70, well, that's negative 35, and 35, that's just 0. So, obviously, this is a root. And the coordinate would be, again, 1 half, comma, 0. It's 2. 1 half, comma, 0. Now, we have to test the next possible root in the depressed equation. And technically, we should test 1 half again in the case that it's a repeated root, because if the root, is a double root, it would show up twice, so it would work in the depressed equation also. But we happen to know that this is a single root, since the curve at the x-axis on that graph wasn't tangent. If it were a triple root, it would be an inflection point, but it wasn't an inflection point either. So there was no case of a repeated root there because of the graph. Remember, tangent's a double root, and an inflection point shows up when there's a triple root. So if we go back to our calculator, again, we saw that it was 7/3 is the other choice. So let's try 7/3. And what I'm going to do is I'm going to try it in the depressed equation. And what that looks like is the following. Noticing that this would be 6x to the third power minus 38x squared plus 86x minus 70. And this is the depressed equation set equal to 0 if we're looking for its roots. Well, what this means is that the next table it just has those coefficients that we just saw there. So you don't really have to write the equation out if you know what you're doing. Just go from here and copy those numbers down in a new, like a subtable you would call it, a subtable. You could also just test 7/3 right out here in the original and see if you get 0 as a root. It would work in the original as well again. But I'm going to test it in the depressed equation so that I get another depressed equation, and the next depressed equation would be x squared. That's the reason I go to a subtable and I don't do it this way. So when I test 7/3 in this depressed equation, bring down the 6, 7/3 times 6 minus 38 is negative 24. 7/3 times negative 24 plus 86 is 30. 7/3 times 30 minus 70, well, that's just 0 because it's going to be 70, yeah, and then minus 70 is 0. So in this case we have another root, and that root is located at 7/3, comma 0. Remember, this is really like the y coordinate. Now the depressed equation from this can be solved using the quadratic formula or by factoring. It'd be 6x squared minus 24x plus 30. We set that equal to 0 to find its roots. Now we can solve this by any means, quadratic formula, completing the square. Either way, when solved, we get x equals 2 plus or minus I. Now one thing I noticed, I went through this whole problem writing x. I mean, clearly it was t, right? The original, if I go back all the way up to the top. But it doesn't matter. I know I'm looking for a time. So at the very end now, I'm just going to write t instead. But I do have my 4 roots now. I've got t equals 1 half as the first answer. T equals 7/3 as the second answer. Then I've got these imaginary roots. T equals 2 plus or minus I. So there's 2 roots here, really. There's one here and one here. So 4 roots because it was x or t to the 4th power in the original function. Noticing, obviously, that the imaginary roots are not really real solutions because we're looking for a time period. So our solutions would really just be these two, right here and here. So example 4 starts with an equation that has fractions in it in decimals of a half. So if we double everything, it'll make this a lot easier. And we have to remember that the rational root theorem states that we're looking for rational roots with integral coefficients, where p and q are integers. So since all the coefficients have to be integers anyway, let's double anything so that the theorem holds true. Now, we take a look at this equation, come up with our p's and q's. Well, there's our p-value, factors of 1, 21, 3, and 7, pretty much. Here, factors are just 1 and 2. So this is easy to write out. So I'll start with 7. So it's 7 over 2 and 7 over 1. Then we have 21 over 2, 21 over 1. 3 over 2, 3 over 1. And then finally 1 over 2, 1 over 1. And these all could be positive or negative. So let's go to our graph right away. So if we take a look at the graph here, we'll notice right away around negative 1.5, right? Negative 1.5. And here it's somewhere as a decimal. This is a little messy though, so I'm not going to know what this is right away. But this one's very, very obvious, obviously. Okay. So that's what we're looking at for this root. Now something to note is that there are no roots in this rational root list that fall between -2 and -3, which makes us think that this must be an irrational root. So this is going to be a binomial conjugate of this number. And we can clearly see they're opposites of each other, it looks like here. So let's see in a moment. This is probably going to be plus or minus the square root of some quantity as a root. When we get the depressed equation, we'll see that we'll probably get a plus or minus here. Alright, so we test -3/2 now in our table. Our table is going to have coefficients of 2, 3, -14, -21. When we test -3/2, here's what you notice. -3/2 times 2 plus 3 gives us just 0 here. Then anything times 0 is 0, minus 14 is -14. This is going to give us 21, and 21 minus 21 is 0. So this is definitely a root. The root's at -3/2 comma 0. Right? Because the remainder is 0. Now the depressed equation is interesting. It's 2x squared, and there's no x. Minus 14 equals 0. Whenever b is not there, this is easy to solve. Just move the 14 over. Right? Because this is not here. Divide by 2. It tells me that x equals plus or minus root 7. That's as we had suspected. Radical 7 is around like 2 and change. It's between 2 and 3. So that accounts for the positive and negative symmetrical roots that we saw on the graph a moment ago. It's positive or negative 2.65 to be close. Okay? So we have 3 roots in this problem. Alright, and we can list those as coordinates. Okay, one of them is a rational root. The other ones come as binomial conjugates. Plus or minus radical 7. Just like earlier, 2 of the roots came as complex conjugates where they had imaginary values.